Hello and welcome to this Alibaba Cloud online course, Dedicated Hardware, Dedicated Hosts, and Bare Metal. We'll be talking about what a dedicated host is, what some of the key features of DDH or dedicated hosts are. We'll be having a quick console demo, and then we'll switch over to look at EBM or Elastic Bare Metal, which is essentially a server without a virtualization layer installed that you can use just like real physical hardware in your own data center. We'll talk about some of the features of Bare Metal. We'll have, again, a console demo of Bare Metal, and then we'll wrap things up with a summary. Let's get started. So we'll start things off by taking a look at dedicated hosts. So we need to talk about what a dedicated host is. So a dedicated host is a physical server that offers an exclusive single-tenant environment. Dedicated hosts can help you address regulatory and compliance requirements and also offer you customizable deployment and allow you to use BYOL, bring your own license solutions on the cloud. You can think of a dedicated host as a dedicated piece of hardware in an Alibaba Cloud data center where you can launch ECS instances. Remember, an ECS instance is a virtual machine. In this case, the dedicated host is a physical machine that you can launch your virtual machines on top of that has guaranteed single tenancy. There are no other users on that machine. There are some advantages to using a dedicated host to run your ECS virtual machines as opposed to running them in the standard multi-tenant environment. First of all, you get more visibility. Your dedicated hosts all have a unique machine ID. You can see your CPU model, number of sockets and physical cores, and you have full visibility of all the virtual CPUs and memory that you're granting to your ECS virtual machines. You also get additional flexibility. There's a wide choice of different dedicated host hardware available. You can create your ECS instances together on the same dedicated host so that they can communicate with each other more efficiently. And you can even create customized ECS instance types with vCPU and memory ratios that are not available in the standard multi-tenant environment. You can also, although it's not mentioned on this slide, engage in what we call CPU over-provisioning, which is where you grant more virtual CPUs to each ECS VM than are actually available on the host hardware. This can help you achieve better CPU utilization of the host's underlying real physical CPU, since most of your VMs won't be running at 100% CPU usage all the time. Anyway, we'll talk more about that feature later. So let's now take a closer look at some of the features of dedicated hosts, or DDH. So what is DDH? And more importantly, what's the difference between ECS and DDH? Well, it's actually pretty simple. There is no difference. DDH is just another way to run ECS virtual machines. So normally, when you run an ECS virtual machine, it runs in a multi-tenant environment, meaning that the underlying physical hardware that your VM is running on may be shared with other users. A dedicated host is single-tenant hardware under your Alibaba Cloud account where you can launch and run ECS VMs. So it's a hardware environment that's guaranteed to be reserved for you and not shared with any other user. Okay, in that case, what's the difference between DDH and Bare Metal? If you're familiar with EBM, Elastic Bare Metal, another Alibaba Cloud dedicated hardware solution, you'll know that Bare Metal is also a non-shared hardware environment. So what's the difference between Bare Metal and DDH? Well, with dedicated hosts or DDH, on top of the physical hardware, there's a hypervisor layer. So you can run virtual machines on top of that hypervisor layer. So you can launch ECS instances directly on top of the DDH's hypervisor. With Bare Metal, there is no hypervisor layer. When you're running Windows or Linux or whichever operating system you prefer on the Bare Metal hardware, it is running directly on top of the hardware. It is not running as a virtual machine. It is running as the host operating system on the Bare Metal hardware itself, just as though you had installed Windows or Linux on a physical server in your own data center. So that key difference is whether or not a hypervisor is provided. Both DDH and Bare Metal are dedicated hardware offerings. The difference is that Bare Metal has no hypervisor, so you run directly on the hardware. DDH, on the other hand, does have a hypervisor, so you can launch ECS virtual machines on top of DDH directly. So what are some of the key features, again, of DDH? Just to reiterate, you get a dedicated physical machine on which you can launch multiple ECS virtual machines. You get additional information about the physical host, its ID number, its real resource counts, its real physical attributes such as unique machine ID, CPU core count, socket type, CPU model, etc. And you get a nice overview in the ECS console so you can see which ECS instances are running on each of your dedicated hosts. A big advantage of dedicated hosts is better budget control through CPU over-provisioning. So CPU over-provisioning allows you to achieve a reduction in cost. How does it do this? Essentially, you can give more virtual CPU cores to each of your virtual machines than you have real physical CPU cores. So you can pretend that your dedicated host has more hardware than it actually does. This is safe to do for a lot of different workloads where CPU utilization on average is low. So for instance, if you're running testing and development workloads, those will have low average CPU utilization in most cases. If you're hosting some type of SaaS platform or hosting business for your customers, the majority of your customers will underutilize the resources that you've provisioned for them, so they'll have low average CPU usage. And if you're using an existing platform like VMware, OpenStack, or Hyper-V, and you're trying to move to the cloud, those products all support CPU over-provisioning. So if you want to keep doing that, if you've already been using CPU over-provisioning in your off-cloud environment, and when you migrate, you want to continue to do it, dedicated hosts will allow you to do that. And again, the key benefit here is a cost reduction over standard ECS. Typically, you'll have a cost reduction over standard ECS of between 20 and 50%. So just as an example here, if you were running your virtual machine on an ECS.C6.large, which has 2 cores, 2 CPU cores and 4 gigabytes of RAM, that would cost you about $28 a month. If you run that same virtual machine on a DDH.R6S instance type, and again you give it 2 cores and 4 gigs of RAM, you can drop the price down to $13 USD per month through CPU over provisioning. Of course, there's one additional benefit here which is not mentioned, which is that you can get better control over the CPU to memory ratio. So you can also adjust the CPU to memory ratio in a way that you're not able to with standard ECS. You can even create your own custom ECS VM types on top of your dedicated host. And there are 3 different dedicated host instance types available right now. The number of physical CPU cores is the same for each one, but the maximum CPU overcommit ratio and amount of available physical memory are different. So there's essentially the C6S, the G6S, and the R6S, which you can see in the table here at the lower right. The C6S has 52 CPU cores. They all do, in fact, but it has the lowest amount of memory available, 180 gigabytes of physical memory, and it allows a 2 times CPU over provisioning or over commitment. Whereas if you were to compare that to the R6S, that allows 4 times CPU over commitment. So you can pretend that you have 416 CPU cores when you really only have 52. And of course, the R6S offers a lot more memory. It has 756 gigabytes of RAM. Another advanced feature of DDH is what we call DDH clusters. This allows you to control access to your environment and to isolate failures. This allows you to put multiple DDH instances or physical machines together into a group. This is great because it means you can improve resource utilization by flexibly controlling CPU over provisioning and optimizing costs across the whole cluster. And it also means you can identify low usage nodes in the cluster and adjust resource assignments to mitigate that. So by having multiple different dedicated hosts within a DDH cluster, you're able to schedule resources flexibly across multiple hosts to balance the load. DDH is available across all 22 of Alibaba Cloud's worldwide regions. So no matter where you are in the world, you can find an Alibaba Cloud data center near you that's offering DDH. You can see here a list of the hardware specifications for the dedicated hosts that are available, both in terms of the number of CPU sockets, physical cores, CPU model, and available number of virtual CPUs. And again, the majority of this hardware is available in all 22 Alibaba Cloud regions, so you can always use DDH no matter what part of the world or which data center is closest to you. This is not a service that's limited to just 1 or 2 regions. This does work in all 22 of our regions. All right, that's all for this section, and I'll see you in the next one. Let's now have a quick demonstration of dedicated hosts from the Alibaba Cloud Console. So here we are in the Alibaba Cloud Console. Let's go ahead and try creating our own dedicated host. So we'll create our very first dedicated host, and we'll try launching 1 or 2 ECS virtual machines on top of that new DDH instance. So I'll click on Elastic Compute Service here. That will take me over to the ECS console. I can then choose dedicated hosts from here on the left-hand side. And there's a Create Now button right at the top. I can go ahead and click that to create my very first dedicated host. So let's do that. I need to choose a region and a zone. Up here at the top, we'll choose Singapore as our region. We'll let the system pick a random zone for me. I'm not picky about the zone. And we need to choose pay-as-you-go this time because I'll be deleting my dedicated host after the demo. So just like with an ECS VM, with dedicated host hardware, you have to choose subscription or pay-as-you-go as your billing type. I'm going to go with pay-as-you-go. And here you'll see there are different dedicated host families available, different types of hardware you can choose from. I want to choose something a little bit smaller. So let's see here, maybe I'll go for Compute Optimized C6. And you'll notice here that this machine has 192 gigabytes of RAM and 52 physical CPU cores, but it allows you to assign up to 104 vCPUs to your ECS virtual machines. That means that this machine allows a CPU over provisioning ratio of 2 to 1. So I have 52 physical cores, and I can have 2 times as many vCPUs assigned to my virtual machines for a total of 104 virtual CPU cores. So let's go ahead and click on Preview. Okay, I need to agree to the terms first. Let me do that. Okay, I'll call it My First DDH. We're buying 1. And then I'll click on Preview to go take a look at my purchase summary. It looks like everything is okay. Pay-as-you-go in Singapore, compute type C6. It's called My First DDH. I'll allow automatic deployment and migration. And we're buying 1. So I'll go ahead and click on Create, and that will start the purchase process for me. This should go ahead and buy our DDH. So we now have 1. And we can return back to the console. I'll close this tab. Let's refresh. And now I have the ability to launch new ECS virtual machines on top of this brand new dedicated host here. I just need to wait a few minutes for this host to start up. If I go to Details, I'll be able to see a list of the ECS virtual machines that are running on this dedicated host. So now every time when I go to my instances list and I click on Create Instance, I'll have the choice to run that instance either on top of my dedicated host or in Alibaba Cloud's general shared multi-tenant environment. So let's go ahead and try running a virtual machine on top of this new host. So I'll click on Create Instance. So just to show you that again, I was here in the dedicated host console, and I clicked on this Create Instance link. That opened up this new tab where I can add a new ECS virtual machine to my dedicated host, which is what I'm going to do now. And you'll see I have this little checkbox here, Associate with DDH, which will, if I check that, it guarantees that my instance gets deployed always to this DDH. If you have more than 1 dedicated host, more than 1 DDH instance under your account, if I restart my instance, it could potentially end up getting redeployed on one of those other dedicated hosts under your account. Checking this box will just make sure it's always on this particular dedicated host. Of course, I only have 1 DDH instance, so I don't need to check this. It won't make a difference. Every time I reboot or restart this instance, it's always going to stay running on this dedicated host. And you'll see that I can choose from any of the standard compute instance families, any of the C6 types. Again, the underlying hardware here of my dedicated host is a Generation 6 compute Alibaba Cloud server, so I can run C6 ECS VM types on top of that. I can also, if I want, let's see, I can see how much remaining vCPU and memory I have on this host. So when I'm creating a new virtual machine, I'm able to see how many resources I have remaining on my dedicated host hardware. In terms of operating system, I can choose from any of the Alibaba Cloud public images for my new ECS VM, just like if I was running it in a shared multi-tenant environment. I can also choose a custom image, a shared image, or a marketplace image. Again, just like with an ECS VM running in the multi-tenant environment. The only real difference here is you'll notice that I don't have a selector up at the top here where I can choose different types of hardware like GPU hardware or FPGA hardware. That's because the underlying hardware of my dedicated host is fixed. I chose Generation 6 compute optimized, so all of my ECS VMs have to be Generation 6 compute optimized. So let's just start type C6 here, a C6.large. That'll use 2 vCPUs and 4 gigs of RAM on my underlying dedicated host. We'll choose that as our first ECS instance to create on this machine. And we'll run Ubuntu 20. Okay, I'll next click on Next, Networking. We'll set up the network configuration for this instance. We'll give it a public IP address. We'll assign it to whatever the default security group is for its current VPC. And we'll attach it to our Singapore vSwitch in Zone A because our dedicated host was deployed in Zone A. That's the zone that the system chose for us. I then need to go through the ordinary ECS instance setup where I choose a password or SSH key, give the instance a name. Let's just go with my DDH ECS inst. I can give it the same host name there. Go to grouping. Okay, I'm not going to save that password. I can apply some tags if I want. And you can see, if I wanted, I could make this instance always run on top of a particular private pool. So a private pool is a collection of DDH hosts that the instance will run on. Since I only have one instance, again, I don't have this private pool function turned on, so we can ignore that. So we'll click on Next, we get a preview, and I'll agree to the terms of service, and then I'll click Create, and that should go ahead and launch my first VM on top of my dedicated host. So I'll close this console again. Let's take a look at the details for our dedicated host, see if we can see this instance starting up. And there it is, it's starting up and it's running on this dedicated host right here. You'll notice I can also see that instance from the general instances overview, regardless of whether my instance is running out in the Alibaba Cloud multi-tenant environment or on my own dedicated host. All the instances in my Singapore region are all going to show up here together in the overview, and I manage them in more or less the same way. I'd only know that this instance here was running on DDH if I look at the details. So when I open up the detailed information for this instance, I should be able to tell that it's running on a DDH. But if I didn't look into the details, I wouldn't actually know that. All right, so let's go log into this instance and make sure it's healthy and working. So I'm going to go fire up SSH, and we'll log in and take a look at this instance. So let me do that. SSH. Oops, excuse me, that was the private IP. I want the public IP. So let's grab that. There we go. Yes, I do want to log in. And sure enough, Ubuntu 20, it's up, it's working. Networking is working. I can ping Google. I can do all that regular stuff that I would do with any other ECS instance. Let's now deploy another ECS instance on that dedicated host. So I'll go back into the dedicated host section in the ECS console, and I'll click on Create Instance again, and we'll try creating another one. So again, we'll do pay-as-you-go. Again, the underlying dedicated host is pay-as-you-go, so I can't choose subscription. All my ECS instances on top of the host need to also be pay-as-you-go. Let's make a bigger one this time. So you can see I still have 102 vCPUs available and 188 gigs of RAM. So maybe we can make a larger ECS instance here. Let's create an 8x large. This has 32 vCPU cores and 64 gigabytes of RAM. And again, we'll just go ahead and run Ubuntu 20. I'll leave the disk information the same. We'll set up networking the same way. We'll give it public internet access. System config, I'll give it a password. I'll choose a host name. First, let me type in this password. Oops, we need to make sure I type that the same way both times. Let's be careful about that. Excuse me, having a little trouble typing this in. There we go, that should take care of it. and I'll call it my DDH big ECS. So this is a bigger ECS instance than the other one. Okay, I won't save that password. Again, we won't change any of the settings here. Let's go take a look at the preview. And I'll agree to the terms of service and click on Create Instance. Okay, great, that happened. Now I can go back to the console. I go to the details for my dedicated host. I can see that I now have 2 instances here, both running on that same physical machine. And just to show you what it's like to have them running together on the same physical hardware, I'll log into both and I'll have them ping each other so you can see how low the network latency is since they're on the same physical host. So I'm still logged in here to my original small DDH ECS instance. Let's log into the big one. So here's his public IP address. Okay, there we go. Yes, I want to save that. Log in, type in my password. Okay, so here's the big instance. Here's the small one, both running on the same underlying physical hardware. And from here, from the big one, I'll ping the private IP of the small one. Since they're in the same VPC group, that should work okay. And you can see that the delay is really, really low. So it looks like the average delay here is well under a millisecond, not even half a millisecond. So really, really fast. These 2 instances can talk to each other lightning fast. So if you're building an application, maybe something like a Kubernetes cluster where all the workers and the master should be close to each other on the network, then DDH would be a great choice because you can ensure, since they're all on the same physical hardware, that network communications between them is lightning fast over the private internet. And of course, now that I'm done with my demo, I can easily go ahead and release this instance and release all of the ECS instances that are running on it. Let's try that first from the DDH console. This may not work. I may have to first go and release the ECS instances themselves. Yes. The selected host cannot yet be released. So first, I have to release my 2 new ECS VMs. Then I will be able to release the underlying dedicated host itself. If you have running VMs on a dedicated host, obviously you're not going to be able to delete that dedicated host until those VMs are either shut down or migrated to a different dedicated host. And you can migrate VMs pretty freely to and from DDH instances, so between DDH instances and even between DDH instances and Alibaba Cloud's public resource pool. All right, so let's go ahead and release this DDH now that we're done with it. I'll say instant release, I'll click OK, and now that hardware has been returned back into Alibaba Cloud's hardware pool, and another user can purchase it if they want. And that's all for the DDH demo. Thank you for joining. Hello, welcome back to the course. Let's now turn our attention to bare metal. We're going to start at the very beginning. What is bare metal? So Alibaba Cloud's bare metal servers are just that. The user, that's you, gets access to the bare metal. These are servers without any virtualization layer installed. Your workloads run directly on the underlying hardware. Bare metal servers give you flexibility, reliability, and in some cases better functionality than you would get from a physical server installed in your own data center. So why is that? You get the flexibility of an ordinary ECS virtual machine, which means you can provision bare metal servers whenever you need, on demand, rather than having to wait for them to come and be delivered like you would with your own off-cloud data center. You get high reliability. The physical server hardware is maintained for you by Alibaba Cloud in one of our state-of-the-art data centers, and you get great functionality. You get all of the speed and efficiency of the physical hardware without any virtualization, but you also get full integration with Alibaba Cloud, so you can use other services like Object Storage Service, like Server Load Balancer, alongside your bare metal instance. And you'll notice that in the picture here on the slide, I have a picture of a bare metal server, and it says X-Dragon on the front. We've made some tweaks and modifications to the server hardware to actually allow bare metal servers to run virtual machines better should you choose to run VMs on your machine. And we refer to that change set as X-Dragon, which you can see is written here on the front plate of this server I have on my slide. So we'll sometimes call this product bare metal. Sometimes it will be referred to as Xdragon bare metal or just Xdragon. So be aware of that if you go through our documentation. So what are some common workloads you might run on a bare metal server? Well, containers are an obvious choice. We have a lot of customers who choose to run containerized Docker container workloads directly on bare metal rather than running those workloads in an ECS VM. This way the containers run closer to the physical hardware and you get better efficiency. Alibaba's own containerized applications within Alibaba Group at companies like Tmall and Taobao are set up this way. We run those container workloads directly on our Xdragon bare metal servers. You can also use bare metal instances for re-virtualization. Because there's no hypervisor on the hardware, you can directly install your own. So if you want to use Hyper-V or VMware or maybe something like OpenStack, you can run that on a bare metal server directly. And bare metal is also a good choice for workloads that require direct hardware access. For instance, perhaps you have an application in banking or finance that needs to use the Intel Software Guard extension or SGX. Maybe you have something that requires the Intel VTX instruction set. Those things can run best on a bare metal server. The key advantages for bare metal are, of course, high performance and fast deployment of containers and third-party hypervisors. But another key advantage is that you can have direct internal access over the Alibaba Cloud internal network to other services like object storage service. So your bare metal instances can be part of a regular VPC network group that's maybe also shared with other ECS virtual machines. That's all for this section. In our next section, we'll have a more in-depth look at some of bare metal's key features. We now take a closer look at some of bare metal's features. So what are the advantages of Elastic Bare Metal, or as it's sometimes abbreviated, EBM? Well, you get the advantages of a virtual machine plus the advantages of a physical machine. That's essentially what makes bare metal such a powerful and useful form of Alibaba Cloud's ECS service. You get elastic access to the service. You can provision a bare metal instance anytime you want. Quick delivery, so you can have access to the machine within minutes. Automated operations and management through our existing Alibaba Cloud management products like Cloud Monitor, and unified I/O, meaning you can access the Alibaba Cloud internal network, join Alibaba Cloud VPC groups, use the internal endpoints for services like OSS, and more. But on top of that, you get the advantages that only come with a physical machine. Strong hardware level isolation, zero functionality loss, zero performance loss, and no hypervisor. And of course, you get complete access to the underlying hardware, so you can do things like use Intel's VTX or SGX hardware functionality. In this table, we compare some of the features of an ECS bare metal instance against a traditional virtual machine and a traditional physical machine. And you'll see that the ECS bare metal instance retains most of the advantages of a traditional physical machine, but also adds some of the advantages of a virtual machine, such as the ability to integrate with the rest of Alibaba Cloud's platform seamlessly, and the ability to be used in a more elastic way than you're able to use a traditional physical server. You can provision a ECS bare metal instance within a couple of minutes, and then you can, of course, if you want, cancel it and return it to Alibaba Cloud when you're done with it, something that you can't do with physical hardware you've installed in your own data center. Another great reason to choose bare metal instances is this Xdragon hardware that we attach to all of our bare metal instances. This is hardware that's intended to help improve the performance of virtual machines that run on our physical servers inside of our Alibaba Cloud data centers. We actually use this to accelerate our own container workloads within Alibaba Group. Essentially, it helps accelerate disk and network I/O, and it takes some of the loads of running virtual machines off of the CPU and puts them on this Xdragon hardware. So you get higher performance, you reduce long-tail delays, you reduce network jitter, you improve network and storage throughput, because network storage and computing are fully decoupled thanks to this Xdragon card, and you get better and more complete network and storage virtualization. So container performance for Docker workloads on Xdragon hardware, so on bare metal instances, is typically about 20 to 30% better than what it would be without this Xdragon card attached to the instance. So here you can see a quick comparison of delay in milliseconds for network and disk for a set of Docker containers on ordinary server hardware and then server hardware plus this X-Dragon card. You can see that there's a pretty significant difference, especially as CPU load on the server approaches 100%. So the X-Dragon hardware keeps the network and disk delay for containers down even as CPU utilization rises. Another advantage, of course, of bare metal plus X-Dragon is that you can provision it in just a few minutes instead of waiting for physical hardware to get delivered if you're using an off-cloud solution. There are multiple potential use cases for bare metal. A common one is to run container workloads. If you want to run, say, Docker containers as part of a Kubernetes cluster, bare metal is a great place to do that. You can use bare metal instances for nested virtualization, so you can easily deploy third-party virtualization tools like VMware, OpenStack, or Hyper-V. You can use bare metal instances in high-performance computing scenarios. You can even build clusters out of them. Some types of bare metal hardware come with RDMA capability, so remote direct memory access. So you can use RDMA-equipped instances to build super high-performance network interconnects between multiple bare metal instances, and then you can run supercomputing workloads like weather prediction, genomics, that sort of thing, industrial simulation. You also get full isolation, so dedicated to hardware that's not shared with anybody else. No cloud-managed hypervisor installed, the hardware is all yours. You can use software that has legacy of licensing requirements. For instance, some solutions do not allow you to use virtualization. Some old-school software licenses still restrict you to running on a single physical host. You can host that type of software safely on bare metal and still comply with those licensing terms. And of course, you get great security. Not only is there no cloud-managed hypervisor between you and the hardware, you can even use built-in hardware special features like Intel's SGX security extensions. Here you can see how re-virtualization would work on an Alibaba Cloud bare metal instance. You'd have, of course, your own software, Linux or Windows, running on the hardware itself, and then I/O tasks are being offloaded to the X-Dragon chipset. You could then run your own third-party virtualization tools right on top, or directly run a container workload like, say, a Kubernetes cluster running Docker containers, as you see in the figure here. So you have a lot of different ways that you can re-virtualize on top of bare metal hardware. As I mentioned earlier, you can even use hardware-specific functionality from within your bare metal instance because, again, you have full access to the hardware. This means you can use things like Intel's SGX for high-security computing. So SGX is designed for data security and privacy in high-sensitivity environments. SGX is a chip-level trusted execution environment that allows your code and data to be stored in an enclave or a private region of the memory that's not readable by applications outside of that enclave, even the hypervisor or operating system running on the host. This allows you to avoid unintended access to encrypted data or sensitive data that belongs to a high security application like something in banking or finance. And Alibaba Cloud is the first company in Asia providing this Intel SGX capability on the public cloud. That's all for this section, and I'll see you in the next one. All right, let's now have a quick console demo of bare metal instances. We'll go into the console and try purchasing one. We're once again back in the Alibaba Cloud console. We're going to try launching a bare metal instance this time, and then we'll try maybe doing something interesting. Let's try to install our own hypervisor on top of that bare metal instance. Remember, bare metal instances do not have a Alibaba Cloud managed hypervisor on top of them, so you can, in fact, re-virtualize. You can run Hyper-V, you can run VMware. I think we should try to do that. So what I'll do is I'll first navigate over to the ECS console. We'll launch a bare metal instance. Let's just run Ubuntu Linux, and then we'll try installing something on top of it like KVM. So we'll try to run a virtual machine inside of our bare metal instance. So the first thing I need to do is click on Instances, double check my region. I want to create my bare metal instance in Singapore. And then I need to click on Create Instance. That will take me over to the Instance Buy page. From there, I can click on Pay As You Go to choose the Pay As You Go bare metal type. That's definitely what I want because I'll be releasing this instance once the demo is complete. Make sure I'm in the Singapore region, and we'll allow the zone to be random. I don't really care what zone this instance gets created in. To select from the bare metal types, I'll click here on ECS bare metal. That will give me a list of the available bare metal instance types in Singapore. You can see there are a few different ones to choose from. I even have the option to go with a standard CPU type or choose a GPU type. The GPU type bare metal instances are equipped with an NVIDIA GPU, or in some cases more than one GPU. So those GPU types would be great for workloads that benefit from GPU acceleration, like virtual reality applications, some types of numerical modeling, and of course machine learning and AI. I don't really need those features for today, so I'll just choose the CPU type, and we'll stick with this default selection here, the Elastic Bare Metal C6 26X Large. And we'll be buying one. We only need one for testing. If I want more than one, I would actually need to click on Increase the Quota here and submit a request to have more bare metal quota added to my account. Don't worry, that's usually a quick process. In fact, before I filmed this, I increased my quota up to 1. It was originally 0, and that process only took about 2 minutes. So I need to choose my operating system first. Let's go with Ubuntu 20. I'll leave the disk size at 40 gigabytes. That's the default. Obviously, in practice, you'd probably be going with a much larger disk for such a well-equipped instance. This instance has almost 200 gigabytes of RAM and more than 100 CPU cores. Normally, you'd have a bigger disk than this, but 40 gigabytes is plenty big enough for a demo. So I'll now manage my networking configuration, assign a public IP address. You can see that we are going to be adding our bare metal instance to a VPC group. So again, bare metal instances, despite not being virtualized, do act like regular ECS instances in the sense that they can take advantage of the other features of the public cloud platform, like the ability to belong to VPC network groups, contact internal service endpoints for things like OSS or the database service, and so on. I then need to make sure my security group and vSwitch settings look okay. They do. So then I'll move on to system configuration, choose a password for my root user so that I'll be able to SSH in later, and then we need to give this instance a name. We'll call it EBM test, and we'll make the host name EBM test as well, so that when we log in, we remember what it is we're logged into. Okay, so I don't need to change any of the tags or any of these other settings here. We'll move on to the preview. Everything looks good. One, pay-as-you-go, Elastic Bare Metal instance in Zone C, running Ubuntu 20. That all looks correct. I'll agree to the terms of service, and then I'll click Create Instance. Great, so there we go. Create Instance. Wonderful. It is now being created. I'll just close this tab here, refresh my instance list. You can see my new instance is starting up. We'll give it a moment to start up, and then we'll go ahead and log in and try installing, say, KVM. Okay, so it looks like the instance is up and running now. It looks like everything's working correctly. Let's go ahead and try to SSH into this instance, and we're going to install KVM, the kernel virtual machine. This is a popular virtualization technology in Linux. So let me just switch over to my terminal window here. Actually, first I need to copy this public IP address onto my clipboard. Switch over to my terminal window, and we'll SSH in as root. Plug in my password there, and great, we're up and running on Ubuntu 20. Quickly, let's make sure that we've updated all the apt package repos. We have, wonderful. The next thing we need to do is pull some information from /proc/CPU info to see whether or not this machine is going to allow us to re-virtualize. Are we really running on the hardware? Are we really running directly on the hardware? Can we really use virtualization features built into our wonderful Intel CPUs that the bare metal instance is supposed to have? So I'll run egrep-c, and we're looking for one or more CPUs physically attached to this instance that support virtualization. So we should get a number higher than 0 when we run egrep. Okay, and we do. We get 104. So again, when I bought the machine, it said that it had 104 CPU cores, and it looks like all of those are showing up as supporting this VMX extension that's needed for us to run virtual machines. We can also go ahead and If we were using Zen or some other system, we could also check under the hypervisor settings in /sys. We'll skip that, and instead we're going to install the kvm-ok command because we actually want to check if our machine is going to allow us to use KVM. So let's do that. I'll try to run kvm-ok. Of course, that will warn me that I haven't installed the toolkit that kvm-ok is a part of. So we'll do that. Great. I'll install CPU checker, and then we'll run kvm-ok one more time, and we'll see what happens. Oh, and while I'm waiting for that, it looks like I need to log back into my Alibaba Cloud account here, so let's just go ahead and do that. I'm going to need to open up my Keyring Manager here and get my 6-digit one-time password, so let's go ahead and do that. All right, there we go. Paste that in. Okay, now we're back in the console. Good, wonderful. So that should fix that problem. We'll go back over to the terminal again. We still need to wait just a moment for the CPU checker tool to install. As soon as that's done, we'll be able to run kvm-ok. And what we're expecting to see is some output that says info and then /dev/kvm exists. This will indicate that KVM acceleration can be used. So we'll just wait a minute for that to finish. Wonderful, so we did successfully install kvm-ok, and we can now check whether or not KVM is going to work. It looks like we can use KVM acceleration on this bare metal instance. Great, so we are ready to go. We could now install VMware or OpenStack if we wanted to. I'm just going to go and directly install KVM. So we're going to need to go ahead and fetch the necessary packages. It's a fairly long list. We're going to need to run apt, let's see, apt install, and then we want qemu kvm, libvirt, daemon, excuse me, gotta spell that right, daemon system. We want libvirt clients, and we want bridge utils. If we wanted a GUI client, we could also install one. There is a client, I believe it's called Virt Manager or something like that. We're going to skip that. We don't need that. So we'll just install these few here. It's actually quite a lot of software, and we'll have to build and enable a kernel module to support this. So we're going to have to wait a minute. So I'll flash forward to when all of this has been successfully installed. All right, so it looks like everything worked. We should be okay to go now. We just need to do one last thing. We need to make sure that we are a member of the correct user groups here. So let me add user, and then I'll add myself, although I'm root, so I probably really don't need to do this, honestly. Let's make sure, oops, excuse me. Oh, excuse me, I made a typo. That should be ID-UM, there we go. Okay, adding user root to the group. Again, as root, we probably don't need to join these groups, but we might as well. And then I'll do the same thing for the KVM group. So we're now part of the KVM and libvirt groups. We should have all the permissions we need to run KVM. Wonderful. So now we can test if our installation succeeded by running vrsh like this. And we should get back this empty list. We didn't get any errors or permission problems. So it looks like everything is working and we're ready to go. If this were a machine that had a GUI, we could install the Virt Manager tool, Virt-Manager, to help us manage our VMs, but it's not, so we'll skip that step. What I'm going to do next is go ahead and install kubectl, which is for managing Kubernetes clusters, and I'll also install alongside of that Minikube, which actually depends on KVM for virtualization services to run the miniature Kubernetes cluster that it sets up. That's outside the scope of this video. I've so far proved that KVM can be installed and virtualization is possible on top of a bare metal instance. So I'm going to just sort of fast forward past the Minikube install process and show you the result once the cluster is already running. So it took some work, but we now have Minikube installed and running. You can see when I run kubectl get all that I do get a response, and the Kubernetes service is running here. We set up Minikube to use KVM, so the Minikube environment is actually running inside of a KVM virtual machine. So virtualization is working on top of our bare metal ECS instance. So let's, now that we've actually gone to the trouble of installing Kubernetes, why don't we just try to run an application on top of it? This is not really related to bare metal itself, The proof of concept for bare metal was just that we've been able to install KVM, so revirtualization is supported. That's all I really needed from bare metal. Kubernetes was just a way to test that, but now that we've got Kubernetes installed, let's go ahead and try deploying a sample application. So there's this great tutorial here on the Kubernetes webpage that teaches you how to deploy a guestbook application with Redis. So what we're actually going to do is set all this up by following along with this Redis deployment YAML file that's provided right here. I'm going to make a copy of that. Okay. And then we'll paste that into a YAML file here. So I'll call it deployment, I'll call it Redis deployment.yaml, or just YML is fine. Paste all of that in. Oops, that did not work the way that I expected it to. Maybe try that one more time. Not pretty. So let's do that again. This time we'll just copy paste the normal way. Let's do that. Okay. Let's make sure that everything in here looks okay. It does. Okay, we'll paste it in. Again, Redis deployment.yaml. Okay, right quit. For some reason those tabs are all showing up really big, but it shouldn't matter, it should still work. So we'll take that and we'll apply this. Well, actually I could have just run apply-f right from this URL. So maybe we'll do that, we'll save ourselves some time. We won't even copy paste it, we'll just apply directly from this online copy of the tutorial. How cool is that? I can actually specify a URL that points to a YAML file when I run kubectl commands. Now if I run kubectl get pods, I can see a running pod. Kubectl get deployments, I should see a deployment. Looks like we're doing good here. The next thing to do is create this master service. Oops, again, we'll do that by just running apply-f. Okay, there we go. Redis master created. Again, start up the slaves. Great. Once again, they provide everything for us, so I can just scroll right by all that detail, run the apply command. Pretty easy, huh? Once you've got these YAML files already created. Okay. One more. Okay, there we go. Okay, so if I run kubectl get services now, I get several different services running. That looks good. So now I need to set up the front end. Again, they've provided a deployment that encapsulates that. And all of this is running inside of that KVM virtual machine where Kubernetes or where Minikube is running. So I should now be able to make sure that everything's running. I can make sure the front end part of this app is running. Actually, it's not. We probably have to download a Docker image first, so we need to wait for that for a couple of seconds. While we're waiting, let's see what else we need to do. Yes, we need to create a service to expose this this deployment on our Kubernetes cluster outside of the cluster itself. So this is, again, not related to bare metal. It's more about Kubernetes. I don't have time to go into a lot of detail, but when you set up an application on Kubernetes, by default, that application cannot be accessed from outside the cluster. You actually have to create a service first that allows access from outside the cluster. That's the next step that I'm about to do here. We're just waiting first for me to have these front-end pods spin up. Okay, it looks like they're running now. Clear my terminal. And now I need to apply this service. The type is node port. That's correct. Node port is how you expose something on a local Kubernetes cluster. If I was using a cloud provider's Kubernetes service, then I'd probably want to use this load balancer type instead. But my cluster doesn't support that, so we'll go with node port. Now I should be able to run kubectl get services again, get services, and sure enough, there's a node port service here running on this IP address. I should then be able to ask Kubernetes, hey, what is the URL for that? And so that is the URL for the service for the front end. If everything is working, I should be able to visit that URL from within my cluster. So I won't follow along with the rest of this. Instead, I'll just run curl, and let's see what happens. Actually, before I do that, let me clear my terminal. Okay, here we go, moment of truth. Sure enough, I get a response back. The application is running. So we successfully booted up a Elastic Bare Metal, or EBM, ECS instance. We installed the kernel virtual machine. We set up a virtual machine to run Minikube, which runs a local Kubernetes cluster. And then we installed and started an application on top of that Kubernetes cluster. And of course, now that I'm done with all of my testing, I can easily log right out of that ECS instance and just release it. Remember, just like any other ECS instance, bare metal instances can be created and released at any time, way easier than provisioning a physical server in your own data center. And just like that, it's gone. Thank you for joining me in this demo. Let's sum up what we've learned so far about both dedicated hosts, DDH, and also bare metal instances on Alibaba Cloud. We'll start with DDH. So what are the scenarios in which you might use dedicated hosts? I would say there are three major scenarios: cloud migration, security and isolation, and BYOL. Cloud migration because DDH offers an environment similar to what you would get from something like Hyper-V or VMware. So it's not one-to-one, but if you're migrating from a traditional virtualization environment off the cloud, you'll feel very at home in DDH. For security and isolation, DDH is a good choice because you have a single tenant environment not shared with other users. And it's BYOL friendly as well. You can bring your existing software licenses, even for legacy software that requires you to know stuff about the underlying physical host, like the number of CPU cores, because you do have that information when you're running on a dedicated host. A key value here is essentially that you're able to build a private environment on the public cloud. So you can recreate your own private virtualization solution on top of the public cloud using DDH, and you achieve good cost, compliance, and control. You have a controlled deployment onto hardware that's dedicated for you. You can comply with strict security requirements if you're in an industry like finance, and you get good cost control. Not only do you always know how much you're going to spend for your dedicated host, regardless of how many VMs are running on top of that dedicated host, but you can also over-provision CPU resources to achieve better resource utilization and a lower cost per VM. Bare metal, again, this is essentially the same hardware that we use for a dedicated host. The underlying hardware is the same Alibaba physical servers with the same Xdragon virtualization accelerator. The key difference is that bare metal instances do not include an Alibaba Cloud managed virtualization layer. When you run Linux or Windows or some other operating system like FreeBSD on top of the bare metal hardware, you're running right on the hardware directly, no virtualization between you and the hardware, which means you can achieve the maximum performance and also use chipset level features like Intel's VTX or SGX functionality. Xdragon bare metal instances are a really, really good choice if you want to run a Docker container-based workload, say a super high-performance Kubernetes cluster, or if you want to port your existing virtualization solution directly to the cloud. Because, of course, on the bare metal instance, you can add your own VM layer. So if you want to run VMware or Hyperware in a cloud environment, bare metal is the best way to do that. Of course, bare metal also gives you some of the advantages of using the cloud. It's not just a physical server because you can also tie it into other Alibaba Cloud services. It ties into our disk service, so you can make snapshots and backups and images of a bare metal server just like a traditional ECS VM. You can use all the internal endpoints for Alibaba Cloud services like object storage service, so it's essentially the best of both worlds. And that's all for this section. Thank you for joining me. Hello, and welcome to this Alibaba Cloud Academy online course. The topic is Special Purpose Hardware, GPU, and FPGA Instances. We'll be breaking the course into 7 sections, numbered from 0 to 6, starting with a discussion of industry trends and major challenges, then moving on to an overview of Alibaba Cloud's GPU-enabled ECS instances, their core capabilities, and common GPU use cases. After that, we'll talk about FPGA-enabled ECS instances, and we'll have a demo of both GPU and FPGA instance functionality in the Alibaba Cloud console. Afterwards, we'll wrap up with a quick summary, and that will conclude the course. Let's get going. We'll start with an overview of industry trends and major challenges. One of the biggest trends that's taken place in the IT industry in recent years is the shift away from traditional IT, which we often refer to as information technology, and towards something we call data technology. As storage prices drop, a trend from traditional procedure-driven IT to data-driven applications has taken place. Traditional applications are focused more on the logic of the application itself rather than on the amount of data that the application collects and processes. Modern applications are driven by data. Most modern applications focus on data collection and processing to drive insights and to produce actionable intelligence and even to train machine learning or AI models. And as a consequence of that non-linear growth in the amount of data that needs to be processed, there's a shift away from the CPU and toward the GPU. The reason is that CPUs are oriented towards program-controlled computing, which was the primary method of building applications in the traditional IT era. GPUs, on the other hand, are oriented towards numerical computing, which is the main type of computing used in the data intelligence era, in part because numerical computing is well suited to training machine learning and AI models and doing other types of large-scale batch processing. In addition, modern GPU hardware has grown in performance faster than modern CPU hardware has. So what are some of the driving forces that are pushing us away from traditional IT and towards DT, or data technology? Well, part of it is that more data plus stronger computing capabilities generates more efficient data processing techniques and technologies. This means we can rely on data intelligence, which is to say insights derived from collected data, to drive the creation of new services and new business models. New technologies allow us to create new business models, and new raw sources of computing power like GPU and FPGA cards enable us to create new businesses entirely. As you can see in the diagram on the right here, the driving forces in most consumer-facing businesses are, of course, experience and price, as well as preferences, quality, and timeliness of offering recommendations to each customer. Given enough data about user habits and preferences, about the state of your supply chain, about losses and profits, about how to select sites, you can make more intelligent business decisions that allow you to do better as a business, and in some cases even allow you to develop entirely new business models. We've seen this many times over the last few years with the emergence of companies like Uber and the various bike-sharing services that are now available, who are taking advantage of the ubiquity of GPS and 4G cellular networks in order to enable totally new location-based services for the consumer. It's likely that as we continue along the path toward stronger adoption of special-purpose hardware, such as GPUs and FPGAs, we'll see yet more new business models emerge down the road. Of course, no one can predict exactly what those new business models will be like, so the rest of this course will focus on giving you the tools you need to get started with Alibaba's GPU and FPGA hardware and try things out on your own. Let's get started. Okay, let's now dive in and take a look at our GPU-enabled ECS instances. As the title card suggests, these are ECS instances that are equipped with a GPU, so they have a GPU attached. There are multiple different ECS families that have a GPU attached. You'll notice if you look at the middle of this diagram that we've divided our GPU instance families into red, orange, and yellow. We'll start on the left with the VGN5i and VGN6i shown here in red. These are designed for graphics and visualization tasks. They're lightweight instances. They're not designed for really intensive use, but they are a good starting point if you're just getting started with GPU hardware and you want to try things out, or if your application isn't too intensive. You could use these for cloud gaming, VR and AR, real-time rendering, creating, say, a virtual anchor or virtual host for some video application, or you could use these to create a cloud graphic workstation for your graphic designers or other professionals who require GPU hardware. And you'll notice that both of these instances have either an NVIDIA P4 or T4 that is a fractional share. So what does that mean? It means that if you get a VGN5i instance, you have access to 1/8 of an NVIDIA P4 card. So there could be up to 4 users time sharing a single NVIDIA P4. With the VGN6i instance, it's an NVIDIA T4, and you have a 1/4 share of the card, which means, again, you could be time sharing the card with up to 3 other people. So there'd be 4 virtual machines sharing that GPU. That's why these instances are cheaper and more lightweight, but it also means if you're looking for something where you have complete control over at least one GPU card, then you're going to want to look at our instance classes in orange or yellow. Let's now turn our attention to the instances in orange here in the middle. These are general purpose instance families that are designed for machine learning and deep learning, or artificial intelligence. So these are the GN5i, the GN6i, the GN6v, and the GN6e. These are 6th generation ECS hardware, very fast, very flexible, and they have 1 or more NVIDIA GPUs. In the case of the GN5s, you have at least 2 NVIDIA P4s or 8 NVIDIA P100s, depending on the instance that you purchase. For the GN6i, you have a NVIDIA T4 times 4, so you have 4 NVIDIA T4s. A GN6v or GN6e would have 8 NVIDIA V100s. So the hardware available is much more substantial, much more powerful than what you get with the the VGN introductory instances shown in red to the left. And then all the way on the right in yellow, we have our bare metal plus GPU ECS instance classes. These are very heavy-duty machines. They don't have a virtualization layer. So when you run on a bare metal instance, you're actually not running in a virtual machine environment. You're running directly on the hardware. In addition to having multiple GPU cards, the machines shown here in yellow also feature high-speed network interconnects, so they're suitable for being clustered together so you can build your own cloud-based supercomputer. These are really designed for scientific computing, so engineering simulation, genetics, fluid dynamics, high-end simulation and research tasks in industry or academia. And then on top of all this, you have the AI ACC. This is the Axera AI Acceleration Engine. This is actually a toolkit that Alibaba provides that's designed to accelerate machine learning and AI applications that are written in TensorFlow, Caffe, PyTorch, or MXNet. So you can draw on the AI ACC to get even more performance out of your GPU-based instances for machine learning tasks. Here we summarize the technical specifications for some of those instance types that we just talked about. So again, as we move from left to right, we go from cheaper to more expensive, but also from less capable to more capable, with the instances at the far right-hand side of the table having more GPU cards available, more RAM available, better disk I/O, and better network connectivity, as well as more CPU power. So the instances at the far right are really designed for heavy-duty scientific and engineering workloads or machine learning workloads, whereas the instances at the left are great for development, graphics, visualization, and users who are just starting out. And as a general recommendation, if you're just starting out with GPU instances, we recommend you start with one of these smaller types. It's always easy to upgrade later. So again, our lightest weight GPU instance families are the VGN6 and VGN5. These are intended for cloud gaming, deep learning, VR, AR, and industrial design. And the way these work is we use Alibaba Cloud proprietary GPU virtualization technology on top of the GPU to allow the GPU to be split into fractions. Essentially, we allow multiple users to utilize the GPU. So multiple virtual machines running under different Alibaba Cloud accounts can access the same physical GPU device. And the amount of GPU that's available to you, expressed as a fraction, depends on the size of the VGN6 or VGN5 instance that you purchase. For instance, if you purchase a VGN5i 4x large, then an entire NVIDIA P4 GPU is available to you. Whereas if you purchase a VGN5i large, what you have available to you is 1/8 of a NVIDIA P4 GPU. So this allows us to give you a better price because we're able to have the same physical GPU device multiplexed so that multiple users can use it at the same time. And of course, you don't need to worry about security. The GPU virtualization layer isolates each user so that the code or other data that you have running on the GPU is not accessible to other users. Another advantage here of these lightweight GPU accelerated instances is that they offer you more refined GPU computing. What do I mean by that? Well, it's easier to scale how much GPU you're using, how much GPU hardware is available to you, because again, you can utilize fractions of a physical GPU. So when you're using a general purpose GPU accelerated instance, all the models, say, that are part of your AI application have to be scaled up at the same time, which increases costs for you. However, if you're running on a lightweight GPU where you're allocated virtual GPUs, so virtual GPU access, when a single module in your AI or machine learning application, say the face verification model or the NLP model, has to be scaled, no problem. It's easy to scale only the necessary components by allocating more virtual GPU resources to the component of your application that needs to scale up. So you have reduced operations and maintenance complexity when you're using one of these lightweight GPU instances like a VGN5 or VGN6. On the other hand, if you need extremely high performance GPU hardware and possibly even the ability to build a cluster of multiple GPU enabled instances, then you should be looking at the EBM, Elastic Bare Metal, or SCC, Supercomputing Cluster GPU instance types. Here we take a look at the ECS SCC GN6 24x large. This is one of the larger supercompute cluster instances that we have available. This is a bare metal instance, meaning there's no virtualization layer running on this instance. You can directly access and use the raw hardware. It has an Intel Xeon Skylake CPU, actually multiple CPUs for 96 total cores, 8 NVIDIA V100 graphics cards, an RDMA network with 50 gigabit per second capability and 2 microsecond latency, and VPC network performance of up to 30 gigabits per second at 4.5 million packets per second. So if you're trying to do a scientific or engineering application that requires a GPU, the Supercompute SCC GN6 instance type is a good choice. One of the core advantages for the SCC instance types is the built-in RDMA network. So if you're running an application that requires really high-speed access to data in memory and you want to perhaps scale that application across multiple physical machines, then you're going to need a way for those machines to access each other's memory contents without too much CPU overhead, and that's what the low-latency RDMA network makes possible. Of course, at the same time, the supercompute instances can also connect to a regular Alibaba Cloud VPC network group, so you can communicate with all the internal network endpoints for other Alibaba Cloud services, like our OSS object storage service. So RDMA stands for Remote Direct Memory Access. It's a technology that allows servers to reach into each other's memory and pull data from memory or write data into memory on remote machines without any intervention from the CPU, so without having to make some kind of a system call and get the kernel to read or write memory. It allows the machines to use their combined physical memory as a single large pool of available RAM. And actually, this is designed in a way where it also works with our other storage products like disks, like cloud disks, network attached storage, object storage service, and even RDS databases. So it's possible to pull data from multiple Alibaba Cloud systems directly over the RDMA network. This eliminates external memory replication and context switching overhead, which frees up memory bandwidth and CPU cycles to improve application performance. There's 3 different billing methods available for GPU-accelerated instances. There's various ways to pay for them. There's subscription, in which you pay upfront, preemptible, in which you temporarily create a GPU-enabled instances by placing an hourly bid. If the market price of the instance per hour is lower than your bid, then the instance will continue to run. If we start charging more for the instance per hour, perhaps because of higher demand, then the instance will stop running. And then there's reserved instances. This is a special hybrid between pure pay-as-you-go and subscription, where you can pay for a reservation, which you can think of as like a token or a coupon that allows you to launch ECS instances in the future at a lower rate than the normal pay-as-you-go rate. And there are discounts available based on the type of subscription or reserved instance that you buy. For 1-year subscriptions, it's about 85% of the normal monthly price. So that's about a 15% discount compared to monthly. 3-year subscriptions, the discount is from 30 to 50%. For 5-year subscriptions, the discount can be up to 65%. So again, the longer you plan to hold the GPU instance, the cheaper it becomes. And you do get better discounts in newer regions, like our China Zhangjiakou region or our China Hohhot region. All right, so just to summarize, the GPU accelerated instances that Alibaba Cloud offers are just ECS, Elastic Compute Service instances, with GPU cards attached. They're mainly used for general purpose GPU acceleration tasks in graphics, rendering, simulation, machine learning, deep learning, etc. There are 4 basic GPU instance types. There's lightweight, which are designed for development scenarios, VR and AR, online gaming, that sort of thing. There are the general purpose GPU ECS instances, which are designed for moderate to heavy GPU-based workloads, think machine learning. Then there's ECS bare metal, which is an ECS instance where there's no virtualization. This is the GPU instance class you'll want to use for extreme performance. And then SCC supercompute cluster GPU instances, which are bare metal instances plus stronger network capabilities. So these have multiple high-speed network interfaces and they support RDMA. So if you're looking to build a supercomputing cluster for a task in industrial simulation or weather prediction or some other high-end scientific computing workload, then you'd be looking at the SCC type of instance. The core functionality we're providing here is general purpose GPU acceleration for a wide variety of different scenarios. So that's things like deep learning, video encoding and decoding, video processing, which means transcoding, so changing video formats, scientific computing, graphics and visualization, cloud gaming, and many more scenarios. That's all for this section. See you in the next section. Core capabilities. This is one of the shortest sections of the course. In fact, it's only one slide, but I feel it's important to summarize what the real capabilities are of the GPU instance types. Why would you need this type of instance? So there are 4 key capabilities, key advantages, if you will, of GPU accelerated instances. There's immense computing power, high network performance, high performance storage, and multiple GPU VRAM specifications. So let's look at each of those one by one. First, we'll start with computing power. A single GPU is a massively powerful compute engine. A single GPU on an Alibaba Cloud ECS instance can achieve up to 125.6 teraflops single precision and up to 62.4 teraflops double precision. So what is a teraflop? Well, it is a trillion floating point operations per second. So essentially, a GPU can do hundreds of trillions of mathematical operations a second. High network performance. Alibaba Cloud GPU-equipped instances have very high network performance. The figures here are for 6th generation GPU-equipped instances. These instances will have a 6 in the name. They can achieve up to 4.8 million packets per second and 25 gigabits per second on a single network interface, up to 50 gigabits per second with 2 microsecond latency for the supercompute instance types, which have an attached RDMA network connection. High performance storage. All Alibaba Cloud GPU-equipped ECS instances offer direct access to petabyte-level storage with millions of I/O operations per second supported by enhanced solid-state drives and CPFS. And of course, there are multiple GPU VRAM specifications, so you can select the correct GPU configuration for your workload, up to 8 graphics cards and 256 gigabytes of VRAM, or down to 1/8 of a shared graphics card and 1 gigabyte of RAM. And of course, this is all coupled to the standard advantages of Elastic Compute Service, rapid deployment, purchase on demand, flexible payment methods, robust infrastructure. The uptime SLA for ECS is industry-leading, guaranteed flexibility and stability, and seamless integration with all other Alibaba Cloud products over the VPC internal network. That's all for this section. See you in the next one. Let's now turn our attention to some common GPU use cases. There are now a wide variety of different businesses using GPUs in production. Of course, the biggest field where we hear about this the most is artificial intelligence. GPUs are being used for traditional statistical machine learning tasks in fields like IoT, Internet of Vehicles, smart healthcare, and fintech, but they're also being used for deep learning. Of course, the most popular deep learning toolkit out there is TensorFlow. TensorFlow does benefit from GPU acceleration. Deep learning tasks in which GPUs are being utilized include optical character recognition, speech recognition, speech synthesis, natural language processing, image recognition and face detection, and more. Of course, that's not the only place where GPUs are used. GPUs have been used for a long time in graphic design for both real-time rendering for VR and AR and cloud gaming, as well as non-real-time rendering for things like architectural settings or movie rendering. And then, of course, GPUs have been a part of graphic workstations for many years and will continue to be into the foreseeable future. GPUs are also seeing use in scientific computing, from petroleum exploration to engineering simulation to weather forecasting to genetics and pharmaceuticals. And then a new application area where GPUs are coming into use is in GPU accelerated databases and sort acceleration. This is a relatively new application of the GPU that's beginning to see more and more use. There are already some open source database engines that support GPU acceleration. Of course, the biggest driver of GPU adoption is artificial intelligence, and artificial intelligence is being used across a wide array of different industries. We're going to focus just on 4 here. We'll talk about large internet companies, autonomous driving, furniture and lifestyle, and industry and service. So big internet first. In the internet sector, artificial intelligence is now being used for things like review, identification, and classification of user-generated content on social networks, as well as for natural language understanding, sentiment understanding, and content recommendation to drive user engagement with those platforms. In education, AI systems are being used for review, evaluation, understanding, and recommendation of course material. And in retail and finance, AI systems are now being used for verification, identification, and classification tasks. In finance as well, systems are being used for anti-fraud purposes now, too. Autonomous driving, of course, there's a lot going on there with AI, but the big driver is, of course, computer vision techniques, which are being used to develop a picture, a coherent picture of the environment around the vehicle that can be used to safely steer it through a variety of different scenarios, whether there's pedestrians or road work or whatever other situation is occurring that the vehicle needs to be aware of. Furniture and lifestyle, home security, so verification and identification from video feeds, CCTV camera feeds, smart interaction with devices in the home. Think about Google, Apple, and Amazon's products such as Alexa that are now being used to allow you to interact with items in your home. Alibaba has a similar product called Tmall Genie. I have one of these in my house. The Tmall Genie lets me interact with certain other items in my home, like smart light bulbs. And then, again, in the furniture and lifestyle category, AI is being applied to personal care and health problems for things like health guidance and disease prevention. In the industry and service sector, AI applications are finding use in warehousing and logistics, both for storage, in predicting demand for goods, and in optimizing routes for delivery vehicles and delivery personnel. AI solutions are being used in the medical and health industries for speech recognition and synthesis, natural language processing, knowledge graph building, identification and OCR systems, and other data processing tasks, as well as, increasingly, diagnostics. In security and public services, AI is being used for verification, identification, retrieval, understanding, and building knowledge graphs from sensor data and camera data that's picked up from security systems around cities and urban areas. In business and finance, customer flow analysis and customer loss prevention are critical applications that are beginning to adopt machine learning and AI techniques. And then in film and entertainment, AI is being used both to generate and to detect deep fakes, as well as to be used in other tasks like image synthesis and natural language processing. Of course, the type of GPU instance that you choose is going to depend on your use case, your usage scenario. If you look at the graph here on the slide, on the vertical axis we have GPU power, lower down on the axis is less GPU power, toward the top of the axis we have more GPU power, and then from left to right we have CPU and memory resources, with the left side of the graph requiring the least CPU and memory resources, and the right side of the graph indicating the most CPU and memory resources. So if you look in the lower left quadrant of the graph, you have applications that do not require a lot of CPU, memory, or GPU power. These are things like cloud gaming, virtual reality, 3D reconstruction, and maybe AI technology teaching and experimentation environments. These things will run just fine on a VGN 5i. In the upper left quadrant of the graph, you find things that require a lot of raw GPU power, but not as much CPU power or traditional RAM. These would be things like large-scale video transcoding or image recognition and reasoning tasks, which can run almost entirely on the GPU card itself. These would run great on a GN6i, GN5i, or GN6V. And then in the right-hand side of the graph, we have things like speech synthesis and speech recognition, which require a lot of CPU and memory, not so much GPU, only moderate GPU computing power is required. These would run fine on a GN6i or GN5i instance with a less powerful GPU, but a more powerful CPU configuration. So take a moment to look at that chart, familiarize yourself with it. The application that you're going to run is going to determine where you fall in this space. Let's now take a look at a common workflow used when developing a new AI business. So you start out with experimentation and research. This is the technical innovation phase. This is where you come up with a way of doing things. You develop a new model that you think is going to solve the problem at hand. Then you move on to development and training. This is the engineering phase. You form an efficient routine through repeated practice and repeated tuning. You start training your model, you start collecting data, gauging the model's accuracy, really going through the model development lifecycle. Then you move on to deployment and inference, the product creation phase. This is where you take your model and you deploy it into a production environment and start using it to make real, valuable business predictions. If a new method requires a large number of input cases, in general, the AI training process will require a large amount of data, so keep that in mind. Also, in general, in AI and machine learning, it's true that the more data you have, the more accurate your model is going to be. So you should be trying to collect as much input data as possible. The key message here is that AI business equals experimentation plus training plus deployment. Of course, just having GPU capabilities isn't going to be enough to build a complete AI system end-to-end. You also need to collect, transmit, and process data, and Alibaba Cloud has tools to help with all of those processes. So speech data, social media data, data from robots and IoT systems, video, audio, and image data, and even data from self-driving vehicles can all be collected using systems like our data transport service, our leased line service, our various network connectivity services that are built into our VPC private network infrastructure, and tools like OSS replication, which allows you to take objects uploaded into our object storage service and seamlessly replicate them across multiple different Alibaba Cloud regions. Once you've got your data safely stored, then of course it's time to start processing it. To help with that, we have a variety of tools. For batch processing, we have DataWorks and Max Compute. For raw storage, we have things like CPFS, our high-performance file system, NAS, which is network-attached storage, so essentially shared files and folders, and then more traditional storage like our cloud disk, which is a type of block storage, or OSS, our object storage service. Once you've stored and processed the data, you can begin training your model. For that, you can use ECS bare metal instances, GPU-accelerated SCC instances, regular GPU-accelerated instances, and of course our AI ACC machine learning acceleration toolkit, which can help you to accelerate models built in Caffe, PyTorch, MXNet, or TensorFlow. And then, of course, all of this can link into our Kubernetes and EMAP-reduced services. So if you have a custom application running on Kubernetes, or if you want to use Hadoop, that's what EMR lets you do, it lets you run Hadoop, then you can tie GPU computing capabilities to Kubernetes or to Hadoop through those two services. And then when it's finally time to deploy or launch your model, we have GPU-accelerated instances that are suitable for running inference and reasoning tasks based on an already completed, already deployed model. And you can, of course, tie this into things like API Gateway to deploy a public-facing HTTP API and auto-scaling, which can help you to scale your inference or reasoning system up and down with user demand. That's all for this section. See you in the next one. Let's now turn our attention to FPGA-enabled ECS instances. So FPGA is an acronym. It stands for Field Programmable Gate Array. And unlike a GPU, the actual internal wiring of the FPGA can be programmed, can be changed, such that the FPGA acts like a custom computer chip. When you program an FPGA, you're actually changing its internal wiring to turn it into a special purpose chip that can perform a particular task. FPGA hardware is suitable for a wide variety of tasks, including image transcoding, genetic computation, data encryption, video compression, hardware emulation design, and also some types of deep learning workloads. We offer two types of FPGA cards. We have our F1 instance class, which uses Intel FPGA hardware, and also our F3 instances, which use Xilinx FPGA hardware. Which one you choose is largely a matter of personal preference. If you're more familiar with Intel FPGAs, you should choose the Intel FPGA. If you're more familiar with Xilinx FPGAs, then you should use the Xilinx FPGA hardware, which you'll find in the F3 instance class. Because the FPGA is essentially a reprogrammable computer chip, you can use it for almost anything, but four of the more popular scenarios are shown here. We'll start with live video transcoding. So, of course, this is something the FPGA can be programmed to do quite well. You can use the FPGA to do real-time transcoding of 4K, 2K, and 1080p video streams. FPGAs can provide very high-performance streaming and transcoding functionality for live video applications. Then there's artificial intelligence. FPGA hardware provides the ability to train new custom AI and machine learning models that are difficult or impossible to implement efficiently on commodity CPU or GPU hardware. So if you have a special purpose-built machine learning algorithm that's not going to run efficiently on a GPU or a CPU, then you can consider trying to run it on an FPGA. FPGAs are also great for chip design and prototyping, since you can take your chip design and program the FPGA to behave in a manner identical to what your final fabricated chip is going to be like. So it's a great way to do integrated circuit design and prototyping. And then database acceleration. So some modern database engines can now use FPGAs to implement highly efficient sort, search, and hash functions. So you can use FPGAs to accelerate database access. That's all for this section. In the next section, we'll have a live demo of both GPU and FPGA-equipped instances. Okay, now it's time for the fun part. We'll be having a GPU hands-on demo. We'll be going into the console, buying ourselves an ECS GPU instance, and running some simple programs on it to see what the GPU can do for us. We will be skipping FPGA cards in this course because setting them up requires special background knowledge and is fairly complicated. We'll focus on the GPU instead. So let's go ahead and get started. Alrighty, so we're here in the Alibaba Cloud console. I'm going to go ahead and click on Elastic Compute Service to go over to the ECS console. From there, we'll be able to purchase a GPU-equipped ECS instance. I'll go to the instances list here, choose the region that I want to use, which is Singapore. We'll use Singapore for this test. And I'll click on Create Instance, which will open another tab that takes me over to the Buy page. From here, I'll check Pay As You Go. I'll leave the zone within Singapore as random. There are 3 zones available in Singapore. I don't really care which one I use. And then for my instance type, the architecture, I'll choose Heterogeneous Computing, which is where our FPGA and GPU instances are listed. And then I'll choose Compute Optimized Type with GPU. I'll just pick the first instance from the list here, which is GN6B 2X large. This instance has 8 vCPUs and 32 gigabytes of RAM. That should be fine. You can see we also have NVIDIA T4s and machines with multiple graphics cards. But for me, just one graphics card, one V100 is okay. For my operating system, I'm going to go with Ubuntu. If you choose, some operating systems support automatically installing the graphics card software, the GPU driver, as well as CUDA, which is NVIDIA's programming toolkit for GPUs. I'm going to choose Ubuntu 20, which does support auto-installing the GPU drivers and additional tools. If you chose an operating system like Alibaba Cloud Linux, then you would also have the option here to auto-install AI ACC for training and or for inference. These are accelerator toolkits that help you accelerate machine learning applications using Caffe, MXNet, or TensorFlow. I don't actually need that The demo we're going to do today only relies on CUDA, so auto-installing just the GPU drivers is fine for me. I'll choose CUDA version 11. This is the only driver version available for the card on this operating system type, so on Ubuntu 20, so I'll choose that. And then we'll install CUDA's neural network accelerator toolkit as well. Okay, so I'll check to install all of those. I can now go on to the next page, which is networking configuration. I will give this machine a public IP address and allow it to have a peak public IP network bandwidth of 100 megabits per second. I'll need that when I'm downloading CUDA installers. I could choose a lower number, but I want to make things faster. I'll leave the VPC and vSwitch settings at the defaults. Security group can also stay at the defaults. I don't need to make any adjustments there. I will log in using a password. In production, of course, you probably don't want to do that, but for a demo, it's okay. And I'll call the instance GPU test. I'll also make that the host name so that when I'm logged in over SSH, it will be obvious to me which instance I'm logged into. And then you can see down here, this is the script that's going to go ahead and install those three things for me: CUDA, the GPU drivers, and also the CUDNN neural network accelerator tool. I won't actually be using that, but I'm going to let it install itself anyway. And then I'll click on grouping. This is where I can decide how my instance is going to be deployed and where. And I can also make decisions about how to tag it, which will make it easier for me to budget and also limit developer or administrator permissions through RAM. I won't touch any of that this time because we're just doing a demo. I'll click on preview. From here, I can double check that all my settings are correct. I can save this instance's settings as a template in case I want to launch more instances like it in the future. I have to agree to the terms of service, and if I want, I can also make this instance delete itself automatically in the future. I will choose that, actually, just in case I forget. I want to save money on my test account, so just in case I forget, this instance will delete itself after I finish the recording. So I'll click on Create Instance, and that should start the process of booting up the instance in Singapore. Let's see what zone it is. It looks like it's in Zone C, so this will create a new ECS instance in Zone C with a NVIDIA Tesla V100 GPU, and then it will automatically install the GPU drivers and CUDA for me. And that process takes up to 20 or 25 minutes, and it will cause the instance to reboot once. So I'm going to let this go, and then we'll fast forward through that process and come back once everything's installed and ready to go. All right, so after waiting a little while, the instance has rebooted and we should be good to go. All the drivers should be installed. So I'm going to copy the public IP address here. I can see this in the instances list. It's this top IP address here that says internet next to it. I'll click on that to copy it to my clipboard. Now I need to open up a terminal. So let me just pop down here, open up the terminal, and we'll SSH in as root. The default username for Linux instances on Alibaba Cloud is root. I'll then type in my password, and you can see all installed OK. That indicates that the installation process for CUDA and for the new GPU drivers has completed, and we're good to go. I now want to run apt updates, and then I'll need to install some additional helpful packages. I want Screen so that I can have multiple virtual terminals running. I also need Git because I'll be pulling code from GitHub, and CMake, which I'll be using to do the build configuration for some of the code we're about to compile and run. I'll say yes to install all three of those, and in a second I should have all three of those things installed. So let's go ahead and install those and see what happens. That should just take a second longer. We'll wait a moment. And while we're waiting, let me show you what we're going to be using. So the code from the CUDA blog entry, from the NVIDIA blog entry that I mentioned earlier, is here. So actually the code that we're using comes from a blog by an NVIDIA engineer. His code is up on GitHub here under Roger Allen, that's his name, Ray Tracing in 1 Weekend in CUDA. And so I'm going to be cloning into this repository and building and running this code on the GPU. And then his code is actually based on another book called Ray Tracing in 1 Weekend. It's actually by Peter Shirley. He's got 3, Ray Tracing in 1 Weekend, Ray Tracing Next Week, and Ray Tracing the Rest of Your Life. So we'll be taking his implementation from Ray Tracing in 1 Weekend in C++ and running that on our ECS instance's CPU to compare its speed to the GPU speed. So let's go ahead and do that. To do that, I'll be cloning into this repository as well. So let's go back to our terminal, see how things are going. looks like we're good. Let's clear the screen. We're currently here in the root folder. I'm in root's home folder, that's fine. I'll first fetch the GPU code by Roger Allen. We'll go ahead and get that. Oops, get clone, and then that URL. That will get us the CUDA code for the GPU. Then I'll go over to this ray tracing repository by Peter Shirley, and we'll download his CPU ray tracing code. So I'll copy this link here from GitHub, again, back to the terminal, get clone, and we'll clone into raytracing.github.io. So the first thing we actually want to do is build the CPU version of the code, so let's do that. So I need to go into raytracing.github.io. Let me do that. Okay, I think the first thing I need to do in here is actually run CMake. So we'll do that. I think I need to give it a path to build. Oops, excuse me, I really need to spell correctly there. There we go. Build. Oops, I also accidentally created build. We can delete that. I'm going to start build. All right, and then in the build directory, we'll have the make files that we need to run. So here I can just run make. That should go ahead and build all of the stuff that CMake configured for us, including the example code from this book here, Ray Tracing in One Weekend. So it looks like everything's built, and sure enough, you can see all of the helper functions and the example code from In One Weekend, Next Week, and The Rest of Your Life, his 3 books. We're going to be running the In One Weekend code. So let's actually go back to the root of the repo, and we'll run time build in one weekend, and we'll output it to a file called image.ppm. It'll be a ppm file. So let's go ahead and do that. Actually, before we do that, let me make sure that I'm in screen in my virtual terminal, because I might want to go work on the GPU code while we're waiting. Whoops, I was not in the virtual terminal. Okay, so let's log back in. Got to get my password right. Let me do that. There we go. Screen. That will put me in a virtual terminal. Again, I'll go into raytracing.github.io. I've already run CMake and make to build my code. The final code is here in the build directory. What I'm going to do is run that code, and what I'm actually doing here with this time command is I'm going to ask the terminal, I'm going to ask the shell to keep track of how long this takes to run. And I'll put the output into image.ppm, and you can see that the program is now running, and it tells me how many more rays it needs to compute, how much more work it needs to do to finish the image, and I'll just let that run. And I'm in a screen virtual terminal. To quit that virtual terminal, I'll hold down the Control A and D keys, go back to my regular terminal, and we'll open up a new screen session for the GPU code. So now I will go over to Ray Tracing in One Weekend in CUDA, and then I'll run make RT to build the ray tracer program itself. There is a warning, but it should have completed okay, it should be fine. And since this code is running on the GPU, it's probably okay to run it at the same time as the ray tracer code we have running on the CPU right now. But just to make this a totally fair performance comparison, what I'm going to do is go back into that other screen session where we're running the CPU code, and I'll just wait for that to finish. So let's actually just wait for that. I will cut back into the video once that's done. All right, and sure enough, after waiting a while, we can see that our output image took 10 minutes and 55 seconds to process. If I wanted, I could now go ahead and open up a second terminal window and run SFTP, actually, to go ahead and download that image that I just created so that we can have a look at it. So let's actually do that. Whoops, I waited too long and I got logged out. So let's go ahead and log back in, and then we'll be able to proceed. Right, so we're logged back in. I can see my public IP again. I'll just copy that, go back to the terminal, paste it in, type in my password. Hopefully I typed that right. Whoops, I did not. Let's do that again. There we go. And now I am using SFTP, so I can go ahead and copy files to and from my ECS instance. I just ran the CPU code, which is over in raytracing.github.io, so I want to cd into that directory. And further, I ran it from the build directory, so that's where the output image is going to be. You can see there is indeed an image here, an output. Excuse me, the output will be one directory up from where I ran the code. It will be in the root, and you can see indeed there is one called image.ppm. So I'll go ahead and do git. But first, let me move to a good location on my local machine. LCD and SFTP stands for local CD. So that actually changes my directory on my local machine. There we go, LCD to downloads. Then we'll get image.ppm. Great, so we did that. It's quite a large file. ppm images are not compressed, so it's a little big, but we downloaded it, and in a minute we'll go take a look at it. But before we do that, let's go run the GPU version of the code. So I'm going to leave the CPU ray tracing GitHub repo, go back up a level, and now we'll go to ray tracing in one weekend in CUDA. So we'll go over there, in one weekend in CUDA. Let's see what's in there. I already ran make-rt to build this ray tracer executable. Now I want to run that executable to produce an output. In this repository, the make file actually has a target that will run this and produce an output for us. If you look in the make file, there's actually a target called out.ppm. So I can just run make out.ppm, and that will run the RT executable and produce a file called out.ppm for me, and it will even time it for me. So let's go ahead and start that off. So that is now running. Let's let that go for a little bit, and just like we did before, we'll come back when that's done. All right, so sure enough, it ran, but it doesn't look very pretty. It's a little hard to read. It looks like, if I'm reading this right, it took about 77 seconds. That's a little bit hard to read. So let's go ahead and actually rerun that by hand, like so. We'll run RT and produce that file out.ppm. And actually, before we do that, we should delete the out.ppm we just generated, since we're doing a second run. So I'll run time, RT, out.ppm, and again, just like we did before, we're going to let that run to the end. So I just want to see if I can get some better looking output from the time command, something easier to read. All right, that's much better. Now we've got something much more readable. So it looks like it took 1 minute and 17 seconds. So not as good as I thought, but still much, much faster than on the CPU. That's almost a 10 times speed improvement. And we didn't do anything to optimize our CUDA code to try to make it better and faster. We just stuck with the default settings. If we optimized it further, we could probably get an even better runtime. Even as it is, 1 minute is a lot faster than 10 minutes. Let's go ahead and download that image file using SFTP, and we'll compare our outputs to make sure they're both okay. So right now I'm in raytracing.github.io. I want to leave that. I want to CD over to ray tracing in 1 week in CUDA, ls, and you can see there's a file there called out.ppm. That's the one I want. Out.ppm, I'll go ahead and get that and fetch that into my local downloads directory. So let's go take a look at those. So if I open up the Finder, image.ppm, this is the one that was produced by the CPU-only ray tracer. This is the one that took 10 minutes and 55 seconds, so almost 11 minutes to make this image. It looks okay. All the reflections are correct. We could change the parameters to try to get a better, finer image, but this is a nice first render. And then out.ppm, which is what was produced by CUDA, you can see they look almost exactly the same. They're pretty close. So it looks like we're getting really good performance out of our CUDA ray tracer. It's almost 10 times faster, and very, very similar image quality, if not identical. So they're very close. You'll notice that the frame is cropped a little bit differently in these two. So there's the balls are arranged differently. There's an extra reflective ball over here. But other than that, they're pretty much the same. So everything worked as you would expect it to. And that's all for this demo. At this point, if you've been following along and you created your own GPU instance, you can go ahead and shut it down and release it. One last thing, if you do want to follow along or try that for yourself, we do have written instructions up on our GitHub page. So if you go over to github.com/AliCloud Academy, you'll find our Alibaba Cloud Academy code examples. You'll want to look at this GPU examples repository here. In there, there's a folder called Ray Tracer. So you can clone into this GPU examples repo and then navigate into the Ray Tracer folder. And there's a document that explains how to run the code, where the original idea comes from, where you can get the the GitHub code that I used in my example, how to run the commands and install everything, and then we even have an example of the ray tracer output. Actually, there should be an image showing up here. I'll go ahead and fix that link a little bit later after the video, but everything you need is right here in this ray tracer directory. All right, thank you for joining me, and I'll see you in the next video. Okay, we've now reached the end of this section of the course. Let's sum up quickly. So Alibaba Cloud offers a wide variety of different GPU instance types depending on your workload. There's GPU instance types for graphics and visualization, for machine learning and deep learning, and for scientific computing tasks. And then on top of that, we have the Apsara AI Acceleration Engine, or AIACC, which can help you to accelerate TensorFlow, Caffe, PyTorch, and MXNet machine learning models. And then finally, again, we have the FPGA instance types, which are suitable for a variety of tasks like image transcoding, genetic computation, data encryption, video compression, hardware emulation design, and some types of deep learning, prediction, or training. So these are very versatile cards that you can use for a lot of different things. We support both Intel and Xilinx FPGAs. And that's it. Thank you for joining me, and I hope to see you in the next course.